Welcome back, my steel design friends. In our previous videos, we spent some time talking about effective lengths of columns and how to calculate the compressive strength for a column in which the top and the bottom were restrained from lateral displacement or side sway. But in reality, most structures don't behave that way. So we need to come up with a slightly different method. And in this video, I'm going to show you how to do that with the alignment charts. So without further ado, let's get started. So if you recall from before, whenever we were calculating the capacity of a column, we were always worried about this factor known as the effective length, or we're looking at some K times L parameter. Okay, we remember that the Euler stress was pi squared E over KL over R squared. It was kind of our theoretical limit for an elastic buckling of columns. This is the Euler stress. Okay, it's this KL, and the K was a reflection of the end conditions of the parameter. So for a pin situation, K was always equal to 1.0. And so, but in the reality is that there were a lot more possibilities. What happens if it's fixed, or what if one end is fixed and one end is pinned? What if one end isn't pinned but is actually free to do whatever? And so we introduced you to a table back in Appendix 7, okay, that was this table C-A-7.1, and so we were looking at a series of cases that looked something kind of like this. So for a fixed case, remember we talked about how the effective length factor on that was 0.5, and that the recommended, which is always something a little bit higher than this, was 0.65. Okay, likewise, we could go and we could pull off, a pin and a fixed, okay, and so that was 0.7 and a recommended of 0.8. Okay, let's see, whichever ones. Here's our theoretical case, our K of 1.0. That was our calibration case that we had. But we also had a couple of scenarios in which I had a fixed support, at one end, and then it was free to do something at the other. Here it's pushing over to the side but not rotating. Okay, here it's, it is being allowed to rotate on this. And you can see that for this case, this is kind of our flagpole case, if you will. The K is actually 2.0 if it's perfectly fixed. Okay, but there are a whole lot of possibilities that exist outside of this table. What happens if I'm only partially fixed? It allows a little bit of rotation, but it's not truly free like a pin. We've got to come up with some better ways to do it, and that's where the alignment charts that you're going to see over on the following pages come in. So there were two of these pages that we're going to look at. Okay, we're going to look at this one, CA7-1 on the next page, and we're up in 16.1-571 in the 15th edition manual to get to this. Okay, and so this is the side sway inhibited case. And you can see that what they do is they have you calculate this kind of pseudo stiffness ratio of columns to beams GA and GB on this scale, and then I can use that to reproduce my K value. Okay, and then if I don't have a brace frame, if it's a moment resisting frame, where the columns and beams are doing all the resistance, there's another table on the next page that uses a different set of criteria. And you can see here my Ks go significantly higher. In fact, we start at 1 and can go all the way up to an infinite K value, meaning that there's no stiffness above, no stiffness below. This free thing is just free to do whatever you want. So you can get some monster K values. Now, for most normally framed structures, generally you're winding up kind of in this range of 1.5 to 3 for your moment frames, just for normal loads, normal arrangements, nothing out of the ordinary. Getting up into here, you got to kind of start thinking about, well, what do I do with my geometry? Is there something else I can be doing differently with the framing to help me with that monster K value? Okay, but if you notice on the page before, in this table, my K was somewhere between 1. So this is my pin case, and you can see that means that my relative stiffness is infinity. Okay, and that's what happens when you're free to rotate and at both ends, and then it gets me 1.0. And if I'm fixed, meaning that there is no relative stiffness, that it's all being absorbed, then 0 and 0 gives me the half. So this is kind of a reproduction of this more general specific, well, more general specific, I say that, for this somewhat limited table that's over here. Now this covers you on a lot of them, but most of the time you're over on these alignment charts here. And so we're going to kind of show you how to use those alignment charts. So the first question that comes to mind is, well, what are GA and GB? So if you kind of look, they've given you a little bit of a sketch here. And basically they're saying we're looking at the column that's between point A and point B. Okay. And if we look at that, then what the GA is, this is the relative stiffness of everything that's happening at the top of the column. So my column is this piece right here. Okay, and then GB is everything happening at the bottom. And so we're going to look at the columns that come in to A and the beams that come into A, and then use those and then compute this GA parameter. And likewise, we're going to look at everything coming into B in terms of the beams being the horizontal guys, and then the columns being the verticals, and everything that they share at that node. Okay, now if you're at the top of the building, it's possible you don't have a column above. If you're framed differently, it's possible that you don't have a beam on one side. You know, if you have a two-story atrium or something like that. So there's lots of combinations that come out of this. All right, so we're going to flip over to the next page, and that's where your formula for G is coming from. And it looks, you know, it's kind of a lengthy formula. It's not too bad, but if you read into this a little bit, it's basically the sum of the EI over L for the columns that come into a node over the sum of the EI over L for the beams that come in into that same node. So it's columns over beams, and you basically add up this EI over L value for each of the members that are coming in that are classified as columns or beams. Now, if the structure is all steel and E is the same, then the E's actually cancel out. And so it's not uncommon to have just I over L for each of the members be reflective of this, what we call kind of this stiffness parameter. Okay, and so that's kind of where we're going with all of this. All right, so if we kind of look at this, you know, we can kind of look at a couple of other simple cases first, and then we'll come back around to that. That if I have a beam that is fixed at the bottom, and then this end is free to rotate and do whatever it wants, remember we were looking at L being the length of the column, but if I kind of draw this, the way that you can kind of visualize what's happening in this and how you can kind of wrap your head around why these K values are changing is, let's go to this case, that if it were fixed here, and this piece moves over, is allowed to move over because it's not restrained, it's now on a roller instead of a horizontal roller, meaning it can kind of drift and do whatever it wants on there, free to rotate it as well, then you can see that if this is fixed, this is almost like a mirror image of itself that exists down below. Okay, and so it's fixed here, and so we're tangent here, and then we're tangent below, and then we could kind of draw this thing out and such that the overall shape of this would be like a column that is 2 times the original length long, right? Because its length for the L is half, and so for this one, K is 2.0. Okay, now that was when it was fixed. If I go to something other than fixed, meaning that it's pinned with, I show this as kind of a partial restraint moment, it's not as much as a fixed moment, but just a lesser moment, then this thing, obviously, this point would drift a lot further, and then when you try to draw that full shape, then obviously your KL goes greater than 2L. Okay, and so that's what we've got to kind of look at as we start to look at this. So this, like I say, it's all because this fixed case is kind of a theoretical scenario, whereas reality is probably more something like this. And this is what the alignment charts are trying to solve. So I've written down some of the versions of the alignment charts from different versions. We're in 15, so that's on that 16.1-571 is the first one, and then obviously 572 is the second one. Okay, and so this one, to my students, I recommend this is a table that you go to enough. Put a tab on this thing and mark this page, because it has not only the K factors for the simple cases, but also has the alignment charts. It's worth having that guy pinned. Okay, all right, so let's take a look, and I'll show you kind of how to use it. We've kind of outlined the procedure and shown you where in the manual you can find it. Is that I have a, maybe for an unbraced frame, a moment frame system, maybe I have this, multiple portal frame, single story tall situation. It has column heights that are 21 feet. Okay, we have columns that are pinned at the bottom all the way through, and then we have a beam that is a W14 by 82 happening up here, and then some point load that is the same at the top of all of the columns. Okay, and so maybe we're after wanting to figure out, well, what do I need to do to size column A here in the middle? So we have a column that comes into a point, and I have 2 beams that come into the point at the top, and there are no beams at the bottom. Okay, and so we're going to assume that the beams are 40 foot long. This is really pretty big spans for these beams. Again, we're not worried about, we're just trying to get an idea of the the way that you calculate these alignment chart values, not so much can this beam hold anything. All right, so 40 feet, 40 feet, and 40 feet, and so we're after this column guy that's in the middle as we start to kind of look at it. All right, so again, the general picture that you're drawing on this is this guy, and that's kind of like that sketch that we saw back in the AISC manual. I'm going to call A as the top, B as the bottom. It doesn't matter. You can flip them. Okay, all we're doing is we're calculating G for each one of these. So if I go through and I do my G for the top, it's going to be the I of the columns of everything coming in to that node A, okay, and then over all of the beams that are coming into the node A. I call it girders, beams, it's the same thing. Now, what do you do if you have a support condition at one of these nodes, which is what we have in our picture back on the previous page. We have a pin at our B node. Okay, well, AISC calls out or says that for those cases, and you can find that if we go back to the manual, this is that second table. All of that information is contained up here on 16.1-573. Up in this paragraph tells you what to do with those. Okay, and it's kind of interesting if you read it. For column ends supported by but not rigidly connected to a footing or foundation, G is theoretically infinity. Okay, but unless designed as a true friction-free pin, may be taken as 10 for practical purposes. Okay, so again, if it were a free pin that was truly frictionless, it would be able to rotate as much as it wanted to go. Okay, it would have an infinite value. Okay, but for instead, now it's saying, well, but in reality, there is no such thing as a frictionless pin or a truly free rotation on a structure. The more practical limit to use is 10. Okay, and you look at that and go, oh my gosh, there's a huge difference between 10 and infinity. Well, if you look on the charts, you can see that it's just a little bit. It's not much because this is not a linear scale. Okay, now, it's not quite logarithmic, but it's definitely not a linear scale on this nomograph. Okay, and so instead of being up here, we're now allowed to come down and use this guy. And so it will make a little bit of a difference, but not much. Okay, and so those are the values that we're looking at. Okay, so for a fixed condition then, okay, you know, our G is taken as infinity, and they say use 10.0. That's kind of the theoretical. That's what the AISC code says. You know, so we'll just make a note per AISC. I showed you the page where that came on. Okay, if the girders are very stiff, okay, meaning that it's like a fixed condition with a column that's coming into it, then you're going to take a G value of 0. Okay, so this would be a fixed support condition, if you will. All right, okay, and so you can see that. So what's happening is if you look at this equation, if the girders are very stiff in comparison to the columns, I put an infinite value in the bottom, that equation does go to 0. And likewise, if I put an infinite value into the top of this thing, you know, meaning that they're very flexible on the columns, well then obviously I get an infinite value on G. So that's all it is. It's just a modeling of the support conditions that you have. All right. So what we're going to do is we're going to take the frame that we have shown, and we're going to take a look at said A572 grade 50 steel. If you want to call this A992, it's fine. It's the same section properties and the same parameters. It's an older example problem. Okay, and so what we're going to do is for our frame, we're going to say that each of those point loads that were happening on our picture, this P load consists of dead load and live load. The dead load on this thing is 55 kips. The live load is 220. Okay, and we have a W14 by 82 beam that's in that frame, and its IX value is 882 inches to the fourth. Okay, so again, one thing to note on that picture, if we look at it, we have called out the direction of the orientation. So this is a strong axis beam. It's in its normal I configuration. Okay, the columns we still got to kind of figure out. Okay, all right, so if we kind of look at this then, all right, we want to size for a column if the plane of the is braced in basically in the X direction, meaning that, you know, if we're looking at this, we want to size this column such that this thing doesn't flex out of the plane that it's in. Okay, meaning that, you know, if we were to consider this in 3 dimensions, you know, maybe in that direction we have a bit of framing or bracing, and then we come over and we look at that, and this is my frame that we're looking at. Okay, so going in that direction, it's not allowed to basically lean over. It's considered as a brace frame. Now, in a real structure, you would consider the K values in both directions and associate that with the L's, as we've talked about, you know, in previous videos about getting that orientation of a column lined up. But for this one, we don't have to worry about that. Okay, all right, so let's go through the example fairly quickly here. It's pretty straightforward once you know how to do it. All right, so we're going to factor the loads. That's the first thing. We'll check the 1.2 dead, 1.6 live, And if I plug all that in, 1.2 times 55 kips plus 1.6 times 220 kips gives me a column capacity of 418 kips. Okay, now the problem that we have is that we don't know what to choose for a length of column. So I can't even begin to go get a size, to get a G, to get a K, to get a length. You know, it's this iterative process that we have to go through. Okay, and so for a preliminary guess, what we're going to do, and as you get more and more experience, you may change your guess on this. Okay, is that we're going to assume for now that K is 1.0. Okay, and this will be grossly incorrect, but for now we're going to start at 1.0, and I'm going to show you the process and how we kind of iterate around through this. All right, so my KLY in this direction is 21 feet in this, and again, we're going to assume that the LY direction is what's controlling in this column. And so if we go through and we do this, then we can go with a 50 KSI steel. We can go back to our table 4-1 and look for our 12s. Look something like this. We're looking for, what was the load again? I lost it. 418 kips, and we're looking for a length of 21 feet. Okay. And again, I'm just kind of guessing that it's a 12, but you could come through and you kind of size it. 21 would be kind of down here in the middle of this thing, you know, kind of in that gap. If we flip over a little bit, probably over in here, if I come at the 21 foot mark, again, when I fall in between, you're allowed to iterate, but a lot of times I just take the one that's higher, okay? And so if we come, we're looking for 418 at 22, and so clearly, if we go over to the next page, that's the first one. Okay, and again, what I've done, if you get the page fully on here, take 22, and this guy, a W12 by 65 at 22 feet long, is 492 kips with respect to the weak direction. Okay, and so that's what we're looking at on that. So that's our Y direction calculation on this. So now that we've got our size selected on this, we can go in. So we got our 491. That was the number that we saw. I guess it's 492 now. It's changed a little bit. Okay, so it's 492. On that guy, its IX value is 533 inches to the fourth. Now we can go in and we can start calculating these G values. Okay, now what I call as G top is actually GA in the diagram, and this guy is GB. And so we go in and we look at this, and so at the top, what we have, if you recall in our picture, is I have one column, okay, one single 21 foot long column coming in here. And so that's what we're going to take a look at in the top. And I have two of the same girders coming in. Now, if these are different lengths, you have to consider the I over L for each one when you do the additive. But you can see the parts. Okay, and so here's my IX for the column and over its length. Now, we've assumed that E is the same, so the E's have all canceled out. And I wrote this as 2 times this value, but in reality, it's probably better to write that term as 882 over 40 plus 882 over 40, right? And if I write it that way, then I know that I consider 2 girders coming in. It's a little less obvious with that value that we're wanting to do that. But that's what we've done. So here's IX over its direction, and we're going to assume that we're bending with respect to the IX. If you're bending with respect to IY, you need to use IY here. So what we've assumed is that all the columns are oriented, you know, this way, and then the girder is coming in and doing something that all the orientations of the members look like that. So the moment you do this calculation here, you've set the orientation. Okay, so this is the strong axis orientation that we're looking at relative to that column and so on. Okay, so I hope that's made sense. So for us, we take GA, that's now equal to 0.58. Okay, and my GB was a pin at the bottom, pin base, and the code says use 10 on that. And so since this is a moment resisting frame, let me flip over. We're going to take a look at the uninhibited scenario in the plane of the frame. So the uninhibited refers to the plane of the frame. I will pull that out just a little bit so we can see a little bit more. Okay. All right. Let's see. And so what we will look at then is I have a 0.58, which gets me, these are in increments of 0.2, so we're somewhere down here right about this third one for A. Okay, and then we go up to 10 on this one. And so if I lay my straight edge over this, we'll go to 10, and we go down to about that third one. And that's literally all there is to it, is we're coming in and we're picking off, you know, a line that is somewhere right around there. Okay, so you can see we're coming in 1.6, 1.8, somewhere around there. I guess this one is 1.8 because it's 1.5, so each increment is 0.1. You've got to kind of watch the units on this. Like these units are 0.2, this is 0.1, this is 0.1. So I'm crossing here at 1.8, and that would be my K value for this guess. Okay, now, so what we did is we go in and we look at, from our sidesway alignment chart, KX is 1.8. So that's exactly what we did on this step. So now we can go in and take a look at, because we've assumed that the plane is fully braced out of plane, we sized it for a weakness in the Y direction, okay? But remember, those tables only work for the Y direction. So what I really have to do is I now have to turn around and calculate the KLY equivalent that we talked about a couple of videos back. So the KL for the X direction is now 1.8 times its length, 21 feet, is 37.8 feet. Okay, and then for my W 12 by 65, and I lost my page again. Let me flip back to that. We're back up in table 4.1 on the 12s. If we come up, so again, we're paying attention to this note. This is what's causing me to have to do this calculation to check the strong axis direction. Okay, and so if I do that, if you come down all the way down to the bottom, the RX-RY ratio is right here. Oops, a little bit more up. It is right here. It's that value right there. And so if I read across, it's 1.75 is the number that we need to do our equivalent. So we've got a size, and we're basically guessing whether or not it will work. Okay, because we sized it for the weak direction. So now if I go through, so that's my 1.75 on this. And again, all we did is we took a shot in the dark on the Y direction of 1.0, and knowing that it would be much longer or much weaker anyway. And then so this KX, we're going to scale it up, and then we're going to calculate the KLY equivalent. 37.8 feet divided by 1.75 is going to give me a length of 21.6 feet on this. And so it turns out that even the KLY equivalent of this columns bending about the strong axis with a KX of 1.8 is actually ends up being almost the exact same length, if you will, on this. Okay, so this would be an effective length of 22 feet. Well, we showed that actually works. We actually got really lucky on this. Okay, but that's one of the ways that we can guess. If you guess a 1.0 on the Y direction as a preliminary guess, and you frame it with respect to the X, this ratio of 1.8 to 1.75, a lot of times you'll get lucky and it'll work out. Okay, not always, but that's why you have to check it, but that's the way that we can kind of design this column, assuming that we have framed it this direction. Okay, so what we're doing is we're basically saying we're not allowing this column to buckle at all out of plane, meaning that there's a concrete wall or a masonry wall beyond it, that this thing cannot bow in any way out of the plane of the paper. We're only considering this plane. Okay, if for some reason you have to consider both, then you have to go through and do a GA, GB in both directions. All right, so where we had that picture that we drew a little bit earlier, kind of down at the bottom, it's not real bright. When we were looking at this picture here, this may be my A node and that may be my B node, and we were looking at, at this frame, in that direction, and these were the beams that went into A. When you turn and look the other direction, it's the same column with an IY value, and now you have to consider the pieces coming in on that direction if we didn't have any framing or any sort of statement like that. So I hope that's kind of made sense to you. The tables are pretty, it's not real difficult, it's pretty straightforward. To kind of wrap it up here, we're going to choose a W12 by 65. Okay, its length is PN of 491 kips. If I run $1.50 a pound on this thing costs a little bit more than $2,000 as kind of a reference on that. So that's how you handle the alignment charts. All it is it's a manipulation on getting a proper K value. Okay, now there are other methods that you can use to do this. We're just doing kind of a direct stiffness method kind of thing. We're assuming everything is in the elastic range. If for some reason you choose a column that gets out into inelastic behavior, and you're looking at something like secondary effects, what we call P delta effects, then you have to do something a little bit different, but we'll save that for a discussion for another day. Here we're assuming we're staying well within the elastic range as we design our structure, and we're not worried about getting out into any of those other ranges and where stiffness reduction becomes an issue. So anyway, I hope that's made sense to you. As always, if there's anything we can do to clarify, please leave us some notes in the comments down below. Otherwise, we'll see you next time. Remember to like and subscribe to the channel, and more videos are coming. We'll talk to you all soon. Thanks for coming. Bye.